Hey class, so I've had a request to make a video about problem 104, the third one on the homework, so I thought I'd go ahead and do that. As you can see in this problem, we have a square with 4 point masses basically, and we're asked to consider a few things. First, we're asked to find the moment of inertia, or the rotational inertia of the object, about this axis at point A that is shown. And second, we're asked to find what the angular speed is about that same axis after it swings to where rod AB is in the vertical position. So the first thing is to try to figure out what it's even talking about with that second statement, right? So what it's saying is, okay, what is the speed as it rotates down into a situation where point A is here, B is here, and then your other two masses would be here and here. Okay, so that's the situation. So it rotates basically, in case you can't see it yet, 90 degrees is what we're looking at. Alright, so interesting, sounds good. Let's start with part A though. Part A, we're asked to find the moment of inertia. And so we have point masses, and so we know that the moment of inertia is going to be the sum of mr squared for all of the different masses. So if we look at that, we have, luckily all 4 of the masses have the same mass, so that's easy, we'll just call it m. So if we go around, if we start with A, its moment of inertia is going to be 0. Then B is a distance L away, the length of this rod, I'm going to call L, the length of each side. So it's going to be ml squared plus, and then if we go over here, call this one C and this one D, the third one would be C, which is also a distance L away, ml squared, plus m, and then the last one is this distance here away. Since it's L and L, we know then that this length here is just going to have the length of L times the square root of 2 because of the right triangle with equal sides. Alright, if you don't remember that, you can prove it using Pythagorean Theorem. But you have L times the square root of 2 squared. So that becomes easy enough. You add those up and you'll have, let's see, 2ml squared plus, well, this looks confusing over here. Let's see if I can erase this L over here just so that's not there. But anyway, what we get is 2ml squared plus ml squared times the square root of 2. And we can pull out the ml squareds if we wanted to. At this point you can plug in your values, but you can see you got ml squared times 2 plus root 2. So that should work out to give you your solution on that part. Oh, wait, I made a mistake here, didn't I? So in distributing my L squared, this would become 2, right? Because it's the square root of 2 quantities squared, so that becomes 2. So you just end up with 4ml squared. So that's good. We'll box it even though it's not the value yet. But now we have to move on to part B. So part B now asks us to determine what its angular speed is, omega, at this point here when it's rotated. So this one gets a little bit trickier, right? So let's scroll down a little bit here. So in this case, we're going to have to look at, or what I'm going to choose to look at is conservation of energy. Alright, so potential energy initial plus kinetic energy initial plus any work done by non-conservative forces is equal to whatever final energy we have. Alright, so in this case, if we look at this, we're going to start with some gravitational potential energy. Our initial kinetic energy will be 0. Our work done by non-conservative forces will be 0. And our final potential energy will be 0. So all we're going to have is gravitational potential energy that we start with is going to be equal to our kinetic energy, which our kinetic energy we can go ahead and observe that's 1/2 I omega squared. So we know I, so if we can find our potential energy, we should be able to determine what our omega is. So the challenge here is looking at how things move. There's a couple different ways to approach this problem. What I'm going to do is I'm going to look at how far each individual mass moves. So if we consider mass A, let's track these masses actually to make it clear. So A stayed here, B went down here. This one that we called C up here is now in this location. The one we called D here is now in this location. Okay, so let's try to determine how far each of these masses has moved. So, to get the potential energy. So, the distance moved, or the above where they started, A ends at the same height where they started. So just to help you see, if we call this, well, we'll call this location, or initial location of 0, we can see how far they all move relative to that. So you see that line then is now here. So you can see that A started on that line and ends on that line, so it has no change in gravitational potential energy. B started on that line and is now a distance L down, so it's going to have a gravitational change in energy of mg times L. So that's from B. Then we can look at C. So mass C starts up here, a distance L above that line, ends on that line, so it too moved a distance L. So you have mg L for C. And then lastly we have D, and for mass D, if you notice, it started a distance L above and moved a distance L below, so it actually moved a distance of 2L. So maybe I should start with its potential energy that it has when it starts then is mg times 2L. Okay, so you can see that in total, that's how far it moved. It moved a distance of 2L. So if we add these all up, what we end up with is mgl plus mgl plus 2mgl. We end up with 4mgl is going to be equal to our 1/2 I omega squared. A second way to look at this is if you look at the change in these two pictures. If you think about the center of mass, which is right in the center of the square, it ends right in the center of the square. It started L over 2 above, ended L over 2 below. So the whole thing moved a total distance of L down. So it had 4 masses, and they moved a distance L down. So you'd get the same thing that way as well. But from here, we should be able to easily determine what our omega value is, because now we know what our gravitational potential energy is that we started with. So we can multiply both sides by 2, divide by I, and you should find that omega is going to be equal to the square root of 8 mgl over I. So go ahead and try that out, and I hope you all have a box-worthy weekend.